Hello, everyone, and welcome. Welcome for today's webinar. Today we're going to talk about something that's a little bit more exciting, at least for me personally. So I'm going to talk about one particular use case of using machine learning algorithm on the HAZOP records. So this is actually something I applied on some of the projects that I did for clients. But please do know that this is not something that's like rocket science in any way, but it's basically trying to use different statistical models to predict the categories of HAZOP records or of those safeguards in the HAZOP records. And so we're not even changing the HAZOP records in that sense. So before I dig in details, I would like to introduce myself very briefly. So I am Paul Chan. I was originally from Hong Kong. So if you look at my resume, you might find it a little bit strange. I have an undergraduate in biochemistry, a Master of Art in English Literary Studies. This is really weird. So basically, after finishing my undergraduate degrees, I couldn't find a job. So I went on and tried to see if I can be an English teacher. So I went for the MA in English. But then when I finished the master, I went for interviews. They all told me that you're overqualified to be an English teacher. But under very weird circumstances, because of my good English, I was invited to be a scribe for a HAZOP and SIL selection workshop in South Korea, in Seoul. So for those that don't really know much about functional safety, the HAZOP and also SIL selection workshops are basically risk analysis workshops for industrial safety systems. So what we try to do at the end of these two workshops are basically find a risk target for the safety system based on specific hazard that we have identified in the HAZOP workshop. So within the workshops, I basically demonstrated how versatile I was. Like I was able to understand a lot of the principles and also know how to do and learn how to do, basically learned how to do the quantification of risk and also reading those piping diagrams within those 2 months when I was in Seoul. So they hired me as an engineer afterwards. And after joining exida, I was very heavily involved in terms of a lot of the probability modeling, the mathematical models using Markov models for different safety systems. Basically, we're trying to calculate the PFD average, probability of failure on demand average, using Markov models. And these kind of SIL, we call them safety integrity levels, that are basically trying to check whether the probability is going to breach that particular safety level for these safety systems. And because of that, I was basically recognized as being very competent. So I was transferred here to the US. And after coming to the US, I start out to do a lot of work on cybersecurity audits, and also get into alarm management projects. So alarm management is about the data of all the alarm configurations within the industrial control systems. And that's why I constantly need to face databases. And because of that, because I need to deal with these alarm data, I need to know data science. I need to know how the data clean. I need to know how to parse those data. And then I started to realize that I can actually use some machine learning algorithms for my daily job, for some of the work that I do. And I realized that I really enjoy doing data science and machine learning techniques and apply them for a better industrial control system in that sense. So that's the basic gist about myself. As for exida, so we are a company basically provide guidance to our customers. We are basically a consultancy in a sense. All of us are consultants. We scatter around the world, and we provide services based on the IEC standards and ISO standards or ISA standards for 3 different fields: functional safety, alarm management and cybersecurity for industrial applications. And I myself is actually part of the committee member for the ISA standard for alarm management in terms of how to manage alarm data and also how to derive those policies for these kind of alarm management systems, or also help the clients to set up these kind of systems in a sense. So in terms of the product that we basically provide to our customers, we provide 3 different services. First of all, we have our own software. I mentioned to everyone that I did Markov modeling. So there is one module within our tool, Excellencia. The module is called Silver module, which basically is using Markov model to calculate the PFD average, and also with other kind of requirement to based on IEC 61508, the functional safety standards for basically calculating seal levels in that sense. Safety level in that sense. So with that software, you don't really need to understand a Markov chain. You just need to understand in a way where to put all the data in, or what brand of valve you're using, what kind of sensing elements you're using. Just put everything in, and the work basically is done by the software in that sense. So you don't need to basically do matrices in Excels, because Markov modeling is basically a transformation of your matrix. So I kind of don't really understand, because in a way that this is actually not that difficult mathematically, but people in this field doesn't do that. And so we are the leaders in terms of seal verification, in terms of seal calculation software in that sense. Other than our software, we also provide certifications for example, safety valves, safety sensing elements, or even safety controllers, PLCs. And we also do certifications for individuals as well. I myself is a certified functional safety professional. And there are also other kind of certificates that we provide to basically assess your competency to work in the functional safety world. And other than that, as I mentioned, we are all consultants. So we basically provide consulting services for everyone for the plants based on the different life cycles in different IEC, ISO, or ISA standards. So that is the main gist about exida. So these are the services we provide. Let's move on to the main dish of today's talk. So before I go into the details in terms of what exactly I'm trying to do with the machine learning algorithm, I do need to lay the foundation in terms of what exactly is HAZOP, because we are using machine learning algorithms on HAZOP, this particular kind of risk analysis methodology. So like any kind of standard that is trying to manage risk, we always have a life cycle. And the life cycle is referring to the whole life of your system. And in terms of functional safety, it is referring to the whole life of your autonomous industrial safety system, specifically the safety system. And also it needs to be autonomous as well. And this is the IEC 61511 safety lifecycle. We've divided into 3 main parts. First of all, we try to analyze all the hazards and risks that are specific towards this particular industrial plant, for example. Like this particular refinery, we're going to review everything to find the specific hazard that are related to this process, or to even to this particular geographical location at this particular site. And then after we have that, we are going to design the whole safety system based on those specific hazards. And then we set out different safety levels that it needs to target and meet based on the analysis, and then we test the design by calculations, by mathematical modeling to see whether they actually meet that particular target. And finally, we move on to the operation side of it. Basically, we're going to look at the matrices on terms of how we're going to, how does the SIS system, the safety integrity system, the safety system, how it actually performs, whether there are a lot of failures and what's actually happening there. And then we're going to do the maintenance and modifications if necessary. And then at the very end, how exactly we're trying to decommission this particular functions, or maybe even the whole, I would say, safety system in that sense. So that is the main gist about the main flow about the functional safety lifecycle that are bounded within the process safety in this sense. And the HAZOP is mainly about the analysis phase of this particular safety lifecycle. Let's go into it a little bit deeper. So like with any kind of engineering project, even a software development project, you have to have a design, basically a scope, a defined scope for that. And then after the scope is defined, we try to move into the identification of these hazards, trying to understand the consequences, and then look at the layers of protection, which is basically a kind of a safeguard. And then we try to derive the basically what kind of safety level based on the frequency of risk and the consequences of the risk that is related to the hazard. And then we design a system with a particular performance requirement based on that particular hazard risk. So, and then we basically produce that particular target SIL level, the target safety level for that particular kind of design function system for that. So that is the main thing why HAZOP is very important, because HAZOP is basically about identifying the hazard and also trying to understand the consequences and then try to list all the safeguards. So this is the main purpose of the HAZOP. How about how exactly HAZOP works? What is exactly the methodology then? So the methodology related to HAZOP, for those who really work in chemical safety or process safety, they would know it by heart. But in a gist, in a basic idea is that we try to divide the whole plant, including the piping and everything, into different units. And then within different units, we try to look at the pipelines and equipment that are associated with one particular process. So what does that mean, one particular process? For example, that one particular process, when you look at all the piping and the reactors and the vessels, it only contains maybe H2S, which is a very, very dangerous chemical in a sense. So when that happens, so we can basically group that particular process into one particular node, and then we try to basically set up a kind of boundary within that node. And within that node, we look at different deviations. So deviations would be something similar to high pressure, high temperature, high level, high flow, or even low pressure, low temperature, low flow, or maybe even low level in that sense. So this is basically a classification of the result of the consequence in a sense, but it doesn't really go into the consequences in that specific within that particular specific details. So let's say within this particular node, this particular boundary that we look at, if we think about high pressure situations, what would actually cause that high pressure situation then? So we need to find the initiating cause for that high pressure. For example, there's a valve within the pipeline. If you close it, it will basically block the piping and then result in high pressure upstreams, for example. And that's a typical block-in situation. And that would be one of the cause for this situation, for a high pressure situation. And then after identifying that particular initiating cause, we're going to move on to the consequences, try to basically detail or the different consequences that's specific to this particular valve closing. For example, there is a vessel upstream, and when closing this valve, you're probably going to overpressure the vessel, and then the pressure might even breach the integrity of the vessel, that it will rupture the vessel, and then you basically have a loss of containment of these process fluid or process gas out into the atmosphere. And that is basically the consequences. And we are also trying to rank the consequences in terms of how serious it is. For example, if the release is going to kill someone, or if the release is only going to cause like first aid injury, or maybe the release is going to breach certain permit environmentally. So that really depends on the situation, and also I would say the capacity of the whole system in that sense. And after we have talked about the consequences, we start to look at different safeguards. These safeguards could be under different categories. So they could be basically instrumentations, reliefs, BPCS system, alarms. And if we realize that based on the design, we don't really have enough safeguards, then we can actually make recommendations to basically design more safeguards, or maybe we can specifically ask the design team to put one more alarms in, or maybe put a SIS in as a safety system in that sense. So the categories of the safeguards, it's actually going to be the main thing, because it is going to be what we're trying to predict in the machine learning algorithm. So let's go into a little bit more details in terms of different types of the safeguards. The first types of safeguards are the alarms. So alarms are usually accompanied with the operator's action. So if the operator can't do anything, then the alarms is basically moot. You don't really need that alarm in that sense. And usually alarms comes in the first events, and then there will be automatic system that kicks in trying to correct the process in that sense. And the second type of safeguard would be those relief devices. So these relief devices are usually relief valves or rupture discs. They are set to a particular pressure to rupture. So for example, if the process is going to have some overpressure situation and it's going to be higher than the set pressure of a relief valve, the relief valve would basically be lifted up by the pressure within this particular piping, within this enclosed process piping, and then relieve that pressure out. In that case, then basically you can avoid that overpressure situation. Another type of safeguard would be the BPCS interlock. So these are referring to automatic functions within the basic process control systems. If you have a little bit older system, you might be basically using a distributed control system, or even, I would say, even older ones, maybe you are using Wonderware, like a SCADA system on different PLCs, like a different programmable logical controllers, then you might even have a SCADA system in that sense. So in the easiest way to understand it is, for example, you have something like a pool, and then when the rainwater gets collected, it's going to fill up in a certain level, and then that certain level you have a sump pump over there, and that when that level is breached over the set point, then the pump will basically start automatically to pump out the water in that sense. So the SIS system works very similarly as a BPCS system. It is basically also contains some kind of sensing elements like high level in the sump pump situation, and then it would pass that to some logic solver or some kind of control logic, and then that control logic would basically pass that signal to start something or to close something. In our example, if we're starting the sump pump, and then maybe in a safety situation, usually it's a closing a valve or maybe opening a valve in that sense. But I have to stress very, very clearly that even the structure or the I would say the basic functionality are similar. All the equipment, hardware, software, and everything, even the design and also the architecture in terms of redundancy that goes into one particular safety instrumented function, the sieve, are very, very strategically being required by the IEC 61508. They need to have, first of all, a seal level assigned to them. And then we need to do the mathematical calculation to see whether they actually meet that particular seal level, that particular safety level in that sense. So everything needs to be in a way that is safety minded in that sense. So this is the screen cap for our PHAX, which is a HAZOP recording software that we sell these softwares. As you can see, there are very clear columns of causes, consequences, and safeguards, and with the categories over there as well. So if you compare this with other kind of HAZOP softwares, usually they don't really have the field to capture that particular safeguard categories. You can say I've got some comment before saying that we don't really need that. That is actually not the case, because the reason why I wrote this program using this machine learning algorithm was because there were two clients basically needed to do this. And one client was basically building gas refineries everywhere in the US, and then they basically need someone to categorize these different safeguards into different categories so that they can send it to different departments for designs. For example, the alarms need to send to the control engineers for designs, the sieves need to send to the process safety engineers, and the relay valves also need to send to the instrumentation engineers, like that, to different departments so that they can push the design out, so that there's like records and everything in a way that the whole managed system is going to work for them. And another use case that I use it for another client was that basically they have this records from a software that they didn't use our software, they use another PHA software that doesn't really have these kind of safety categories recorded for them. So they need that. They basically need that to basically, in a way, to isolate all the alarms that are within the HAZOP records. And usually one HAZOP record can be consisting of more than 10,000, 100,000 of lines out there. So they needed that all the alarm isolated out so that they can basically pass that to the next phase in terms of their alarm management system. And basically I save both clients a lot of times, especially with the first client. I basically saved them a lot of work because they were contracting these kind of manual checking work towards outsourced to another company. So it saved them money in terms of tens of thousands of money in that sense. And for the second client, I saved them basically compressed the time that they needed. Originally, they need a month to go through all these manually, but I just finished everything within 1 or 2 days for them. So there's definitely a use case for this particular classification in that sense. And also, I want to stress very clearly here that we need to have a good idea in terms of the importance of data, because this is actually being communicated across different IEC standards. The IEC standard for alarm management, IEC standard for functional safety, and IEC standard for cybersecurity. They always ask for good records of data so that you can use them to improve your system. In fact, a lot of the field devices, you can even use your field data to derive your own failure rates in that sense, in a way that you don't need to outsource it to a consultancy to do that, if you actually going to keep a good records of everything. And we understand that because we work in all three different worlds, and we understand how different data can interact with each other, are needed of each other as well. So that lays the foundation for the technical detail in terms of the safety background in terms of why we actually need to use some kind of algorithm to do the safeguard types prediction. So the goal of the machine learning algorithm is to basically trying to classify the safeguard types based on those safeguard description, based on those words in that sense. So typically how an ML works, how a machine learning algorithm works is that we get the data that contains both the descriptions of the safeguards and also the safeguard types that we try to predict in that sense. And then we split those data into training data and the test data. So because we have both categories, we have both the features that we try to use to predict the result. So in a way that the machine is trying to learn how to predict the result based on the features that we input into it. So that training model is basically working in that sense. And then we're going to test some data within that training model, basically to see whether the training model has a good accuracy. And we're going to repeat this process again and again so that we can have a higher accuracy, and then we can basically use it and apply in a real world case. And specifically, the algorithm that I'm going to use for this case is called Naive Bayes Classifier. So I'm using the package from the library, Python library scikit-learn. The basis for the mathematical theory behind this Naive Bayes theorem, Naive Bayes Classifier is the Bayes theorem. So all machine learning algorithm, we're basically trying to reduce them into a mathematical problem. It's a calculation for the machines. It's always a kind of numerical reasoning behind the machines in that sense. And for Bayes theorems, basically it's talking about the probability of something based on certain conditions. And that is exactly what we're trying to do. We're trying to predict the probability of the hypothesis H based on different evidences, based on different evidence, or based on different features. Sometimes that's the word features that's used in machine learning algorithm. And in this case, the hypothesis would be the safeguard classification, and the evidence would be the bag of words, which is basically words within the safeguard description in that sense. I need to stress over here that Naive Bayes assumptions, actually, they have two main assumptions whenever we can use the Naive Bayes classifier. The first one would be the independent features among each of the evidence. The second one would be that every feature within that bag of words needs to be of equal weight. So what do these mean? If we think about a text application, because we are trying to figure out how to predict the classification based on text input, right? A lot of the times, these two assumptions don't really work, because if we think about two words, machine learning. Machine means machine, learning means learning. You can be learning, I can be learning, everyone can be learning. So they don't really convey that information until these two words come in together, machine learning. So when these words come in together, a new meaning is born. That means that the machine is learning. So that means that each word is dependent on each other to convey the meaning in that sense. So that's why that is about the independency between different features, between different words. And secondly, about the equal weight problem. This doesn't really work either, usually, for sentences. For example, consider this sentence. There are 50 states in the US. There are 50 states in the US. The word "the" here is only an article. It doesn't really contribute anything to the meaning. So in that case, then it doesn't really in any way that it doesn't offer same importance as other words. It doesn't really have the equal weight as the other words within that sentence. But if that's the case, why can we basically apply this onto our situation then? That is mainly because the languages that use in HAZOP are very highly standardized. We even have a specific IEC standard for that. The IEC standard is 61882. And secondly, if we look at all the descriptions here, none of them is actually complete sentences. They are mostly phrases and clauses. So that greatly reduces the interdependency for each word with another in that sense. We also, about the problem with the equal weight, I'm going to explain and also do some data cleaning and use the data cleaning to basically reduce the unevenness of those weight of each words. So therefore, after all the work that goes in, this classifier is quite accurate when it comes to predictions on safeguard classification, specifically used in a HAZOP situation. So this is the main workflow of the ML algorithm. We load the data, we clean the data, we split the data sets for testing and also for training, and then we loaded everything into the machine learning algorithm, and then we start to use it to predict new data in that sense. So the whole code, if I go through it in details, it's probably going to take a whole afternoon. So what I want to do is only focus on two main things, the data cleaning and also a little bit about the main algorithm as well. If you guys are interested, you're welcome to basically go to my GitHub to have a look. The codes are basically published there, and there are annotations and comments. You can, I believe it's very, very, I would say, user-friendly. Even if you don't understand programming, you can understand most of the sections of what exactly they were designed to do and what I am doing with these codes over there. So welcome to basically check out my GitHub and then have a look of this code over there. But specifically today, I just want to mainly talk about data cleaning and also the main algorithm. As for data cleaning, I want to focus on how exactly I'm transforming a one column safeguard into the description column, which I'm going to pass into the algorithm for predictions using an NLTK, which is library. I'm going to talk about that in details later. And also, I'm trying to narrow down the safeguards classes that I want to predict, and then I'm going to ordinarily encode them in that sense. So what exactly is NLTK then? So it stands for Natural Language Toolkit. So it's basically a Python library. It's a library for computational linguistics. So it has a lot of different uses. Scikit-learn also has some kind of natural language processing capability, but I prefer to use this library because it's a lot more complete than the ones within the scikit-learn library. So I only use 3 different functions from this particular library in this use case. I use the corpus package to remove all the stop words. So what exactly are the stop words? They are usually the articles, a and the, and also the verb to be is MR in that sense. And I'm also going to use the tokenized package to basically blast everything, blast a sentence into individual words, and then store them as arrays within a variable. And this is mainly so that I can pass these kind of arrays to the next step, that I try to lemmatize them. So what exactly is lemmatization? So the main purpose of this is to reduce the influential forms of words into their base forms. Let's take an example right over here for this sentence. The boys' cars are in different colors. When we lemmatize it, it becomes the boy car be in different color. So as you can see, plural forms into singular forms, adjective into its root, a root form, it can be It can be verb or it can be noun. And also apostrophe s would be basically removed, and also these kind of verb form are basically reduced to their basic form. Are basically is a verb to be, so it's basically reduced to be in that sense. So I'm going to talk about why exactly we actually want to do lemmatization and also removing the stop words when I'm going to talk about the main algorithm. There's a very, very interesting, I would say, the main purpose behind every, I would say, shenanigans that we've done here. So after using the NLTK, I'm going to filter for the desired safeguard classes. So in this algorithm, I only want to predict SIFs, BPCS trips, or alarms, or backup equipment. So these are the main categories that I want to predict. And after I have basically cleaned up the category columns, extracted all the data, I need to encode them. I need to encode these categories into numbers because machine can't really understand strings. Rather, it understands numerical values. So even if you talk about Boolean logics, to machines is basically 0 and 1. Everything is about number in this sense. So that's why we need to find a number to represent each categories. In that sense, in this case, it will be in the logs, that would be number 2, alarms would be number 0, and 1 would be the number for backup equipment in that sense. So that is the main flow about data cleaning. What's next I'm going to talk about is the main machine learning algorithm. So let's look at an example right over here. For example, there is a passage or an article, and then what we want to do, or the machine is trying to do, is put the whole passage into a bag, shovel it, break up all the word order between different words. Everything is in a mess, you can say, and exists as like individual words. That's why we call it a bag of words in that sense. And then the machine is going to count the frequencies of each of the word, like this. Listed out all the words and the frequencies of these words within this passage. Now, if we tell the machine that this particular passage is a spam email, and then the machine will basically try to understand it, in the case that when the machine sees that there's a high count of these kind of words, these few words, then it will automatically categorize a new passage that basically associate that with a spam email in that sense. So that is basically the main gist of the machine learning mechanism in this case. It's very simple. It's nothing like rocket science or anything. And that is why I like this classifier, because it doesn't really involve too much math. So it's really quick. It doesn't really take up too much computing power. I don't need to even have like a multi-core to actually run it in a lot of sense. But before we conclude everything, I do need to remind you that a machine doesn't understand words again. So that's why there's a function within scikit-learn that's basically doing the same thing as ordinal encoding. Basically, it tries to encode each unique word with assign one particular number in that, and then basically save it as a list, or you can think of it as like a matrix in that sense. And because we try to assign each unique word with one unique number, that is exactly why we need to do the data cleaning. That's exactly we want to remove the stop words in that sense, because we don't want words like and the or ismr without any meaning in a way that actually going to affect the word counts that we did for this particular bag of words in that sense. If you can see, because the is usually very common within a passage. So they usually tend to have really high counts over there, and they don't really mean anything when it comes to a certain, even to the passage in that sense. It's just a modifier in a way. So in that case, we basically remove the lower weight words and prevent them to basically affecting the accuracy of the ML model. As for another thing that we try to basically lematize all the words, all the passages, is basically because each unique word is indexed as one unique number. So if this is the case, let's go back to our example over here. Think about the sentence over here. If there's another sentence that's called the boy's car is in a different color, then in that case, car and color will be actually counted as different words as the cars and colors. And that is exactly why we don't want these kind of plural forms or any kind of other kind of, I would say, influential forms that's going to screw up this particular machine learning algorithm. That's why we want to reduce them to their very basic form so that the count won't be significantly affected in that sense. So that is the basic gist for the machine learning algorithm. At the end of the algorithm, I even made a word cloud for the alarm classification. So for all the alarm, for all the safeguard descriptions that are categorized as alarm, they have really high count of words have a really large, basically, font in this sense. So naturally speaking, anything that with an alarm would naturally being categorized as an alarm, within the safeguard description in that sense. So if you people are interested to know more, I actually made another fun project, which I also uploaded on GitHub. So this is a salary prediction, which I can predict salaries based on your job level, your education, and also based on your profession in that sense. But I'm using data from basically from a green card process, because during the green card, there's one process within the green card process that the U.S. Department of Labor is going to audit the foreigners' salary based on their work location, based on their geographical location, based on professions, their education level, and also their job level. So that's why it is, I would say, a certified data that's really reliable goes into the model for the prediction. That's what I did. But right now I'm still working on it in a way to basically improve the accuracies. But welcome to check it out. I also plot another graph, or you can say map. This is the map of New York, and I basically plot different salary level based on their zip code in that sense. As you can see, also the problem with the data set is that usually you only get about 100K of data for each year from I would say, the Department of Labor when it comes to green card processes. So the data aren't really complete a lot of times. Like some of these areas, it's just black in that sense. But honestly, I don't think anyone would live in the Central Park unless they're homeless. So maybe that's also the reason why. So if you are interested in other aspects of safety, welcome to basically join our online self-paced training course. We also have online live training course and also even live training course that are held at different venues. Welcome to shoot us an email, follow us on Twitter, go to Facebook or our LinkedIn. And also welcome to basically write me an email and go to my LinkedIn, or maybe even go to my blog and GitHub to have a look in terms of the problems and everything. Therefore, welcome to basically check everything out. I am also going to basically paste my GitHub in the chat for easier access for everyone, I guess. Give me a minute. And basically, welcome to write me an email or connect with me on LinkedIn. I'm really happy to basically answer any questions you have. So let me see. Welcome to ask any questions now, because we do have some time left. I see already a question here. So once you lematize the phrases, what do you do with that data set that helps with the PHA documentation? Can you elaborate on that? So let me show you the code a little bit more. So there, within data science or even data analytics, we never ever try to write over a record. So what I am doing here is, first of all, I load the data set from the HAZOP record as basically assign that into a variable and as a data frame, Panda data frame in that sense, so that I don't really overwrite anything that's from the original records. So after I encode these, basically the encoding is basically introduce one more column within the data frame, and then that shows every number, or it shows basically store as like a matrix within this data frame, so that it's not going to affect the PHA records in that sense. But I basically use that, the encoding, all the numbers is only going to be useful and only going to be understandable by the algorithm itself, by basically the algorithm right here, which I set up a pipeline for that, the vectorizer, and also the multinomial naive Bayes program over there, and then it's basically doing that over there, and then try to predict the classifications based on that. And then after that, I can basically use any kind of data, put that into the algorithm based on the prediction, and then it can basically predict based on what I input into the algorithm in that sense. And that is the main use case for this. I would admit that this is not something that is so big that you can. I do get some impression that some people, when they think about machine learning, they would think about, okay, maybe we can actually do the whole HAZOP using machine learning. I did get questions like that. Can we actually use the whole machine learning algorithm to do the whole HAZOP, or even do the whole CHAZOP in that sense? I would say in the future, yes, definitely. But at the time being, I highly doubt that is possible. One of the main reasons is that for HAZOP records, they are not really shared by other people because they are related to safety informations. And a lot of, I would say a lot of countries list these, especially when it comes to refineries, they list them as national interest, so that everything has to be confidential in that sense, so that we don't really have a big data set or database to draw from in a way that we can basically do that particular testing or do that particular training for the machine learning algorithm. So I have another question here. Effectively, you automate what a scribe would do by going back over the PHA and assign each line to 0, 1, 2 safeguard. Yes, that is exactly what we try to do right over here. But it can sometimes, if the records, they actually have that categories, like what we showcase for our screenshot over here. Within our software, the scribe will basically put things in there. But what a lot of the cases, because they don't really use our software, or maybe they use a software that doesn't really have that functions, this is what we end up with. just a list of descriptions without any categories, and that is basically creating nightmares for the, I would say, the design department in that sense. So I have another question. Is it possible to combine bag of words with a text embedding model to improve robustness? It says, i.e. handling misspells. So I believe there is a function within the, I would say, within the NLTK library that can actually achieve that. So definitely you can do that. However, there are also other software that you don't really need to go through that, because as you can, yes, you know, as you can see, in order to actually use these libraries, you do have to be very well versed when it comes to Python language or even other kind of I would say the programming language in that sense. So there are other software that you can use basically to do the spell check while you scribe, or maybe afterwards you can quickly check. And I also have some kind of queries in the previous few sessions asking about this very similar questions, whether there are some kind of, I would say, complete packages like consumer products rather than actually raw codes that can help to facilitate this situation. I would say right now we do not have that yet, but given that HAZOP is a very standardized process, maybe in the very future we'll be able to see that very soon. But at the moment, even the data cleaning, it can take so long right now because you have different specific cases that you need to handle, especially when it comes to text formatting in that sense. All right, I think that's it for today. Again, well, if you have more questions or you maybe to shine, welcome to send me an email or ask me anything on LinkedIn. Check out my GitHub and have a look. Maybe you have more questions afterwards. I'll be waiting for you, hearing from you guys. Thank you very much for attending to today's session. I guess I will see you next time then. Thank you very much. And have a very great day based on where you are.